Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning about the integral test, another test that we can use to figure out whether or not a series converges or diverges. We're taking a trip on finding all of these tests, taking a look at them and seeing how they all work. Okay, and then we'll be able to choose whichever one can be used or the best one to use for a certain series. All right, so let's see how the integral test works. Okay, so the integral test involves a few conditions that you really should know off the top of your head. So, given that a series where a sub n is positive, continuous, and ultimately decreasing, meaning that at the beginning, it's okay if you have maybe a term or two where the a sub n is increasing, but as you move on toward infinity, it has to be a decreasing function or a decreasing nth term. All right. So that's what we mean by ultimately decreasing. Okay. So something will happen here. If the integral from 1 to infinity of f of n dn converges to a limit L, okay, for L, a real number, then the series will also converge. Okay, so basically, if the improper integral converges, then the series will converge. If the improper integral diverges, then the series also diverges. Now, what's important to know about the integral test is if the integral converges to this value L, that does not mean that the series will also converge to the value L. It just means that the series converges. It does not tell you what the sum of that series is. The integral test cannot tell you that. It can only tell you that the series converges. It cannot tell you what the sum of that series is. Okay? All right, so let's get started. Let's take a look. All right, so we're going to determine whether or not this first series converges or diverges. We're going to use the integral test to do it. So to use the integral test, the first thing we have to show is that this nth term, a sub n over n squared plus 2, is positive. And it most certainly is, we agree. If I'm only plugging in values, positive values, the answer to this is going to be positive. Second, we need to show that it's continuous. And it certainly is. N squared plus 2 does not equal 0, right? So there's no place in the denominator here that would give me a 0. That is included here. It's imaginary. So that's okay. And we also have to convince somebody that it's decreasing. So I guess there's a couple of ways that we can do that. Well, if you want to convince somebody that something's decreasing, the easiest way to do it is with the first derivative test, right? So we can take this and derive it. Okay, so if we were to do that, let's say f prime of n, it's leave the n squared plus 2. Derivative of n is 1 minus leave the n, 2n over n squared plus 2 squared. I want to know where that's 0. That gives me, let's see, we have negative n squared plus 2 over n squared plus 2 squared equals 0. So that would mean negative n squared plus 2 would have to equal 0. So 2 would equal n squared, n would equal plus or minus square root 2. So there's critical values of plus or minus square root 2. The negative square root 2 critical value we throw out because n has to be 1 and only positive values after that. So the question is, what happens if to f prime at square root 2? So if I pick a value for f prime to test, like 2, all right, let's say if I plug in 2 to f prime, it gives me negative 4 plus 2, negative 2. The bottom's positive. So that's a negative answer. So that means that this function would be decreasing. Okay? So f is decreasing. All right? We did that by the first derivative test. Yeah? Okay, so now we can use the integral test. So the integral test says that I'm going to integrate this thing from 1 to infinity, which I'll change to the correct notation momentarily, n over n squared plus 2 dn. All right, or you can change it all to x, whatever makes you happy. So this is the limit then as b goes to infinity of this the integral from 1 to b, n over n squared plus 2 dn. Okay, to integrate this, I need substitution. So I have to let u be n squared plus 2. du is 2n, dn. I need a half here for Beach Boys. So this is going to be 1/2 limit b goes to infinity. We're going to integrate. We'll change the bounds, I guess. We'll make u 1 plus 2 is 3. And then we'll still go to b. b is still infinity, right? It's technically b squared plus 2 up here, but that's still infinity. That gives us du over u. The integral of du over u is the natural log. So this is 1/2. The limit as b goes to infinity. Straight line from u equals 3 to b. The ln absolute value u. So now I'm going to plug in. We have 1/2. We want the limit as b goes to infinity of the natural log of b in absolute value minus the natural log of 3. Well, the natural log of 3, that's some number. The natural log of b is b goes to infinity. You have to remember what the natural log graph looks like. Natural log of x looks like this. So it slowly goes to infinity, but it will get there eventually. So this value here is infinite. So this is infinity minus 3. This diverges. Okay, so the integral diverges. So the series diverges by the integral test. All right. So there's my answer. Okay. All right. All right, let's take a look at this one. So let's try, actually we're going to change this problem, I think. Rather than 1 over the square root of n, let's take this problem away. Just do something a little different. Let's try 1 over n squared. Okay. All right, so we're going to do 1 over n squared instead. So the first thing to use the integral test is, well, first of all, notice that this is not geometric, right? So this is 1 over n quantity squared. It would be written like this, 1 over n quantity squared. That's not geometric. So we can't use the geometric series test. Okay, but here's what we can do. So first of all, this thing is going to be positive. There's no doubt about that, right? N equals 1 to infinity. So plug in any positive number here, you're going to get a positive answer. Is it continuous? Well, it would be discontinuous when n squared is equal to 0. So n would be 0, but n starts at 1. So that's no good. So it's continuous, and then it has to be decreasing. So to see if it's decreasing, let's see. F of n would be n to the negative 2. So if I derive that, f prime of n would be negative 2 n to the negative 3, or negative 2 over n cubed. So that would be 0 at 0. Well, it'd be undefined at 0, right? Undefined at 0. So I can put 0 on my number line, but if I go anything to the right of 0, pick any number you want, plug it into f prime, like 3, anything, it's going to give you a negative number because the top is always negative and the bottom's always positive. So this is negative here, so this is decreasing. So sure enough, it's decreasing. So we can use the integral test. All right, so we're going to integrate this thing. We're going to integrate from 1 to infinity, 1 over n squared dn, which is the limit as b goes to infinity, the integral from 1 to b. Let's just write it as n to the negative 2 dn because we want to use the power rule. Add 1 to the power, divide by what you get. So the limit as b goes to infinity from 1 to b, n to the negative 1 over negative 1, which is the limit as b goes to infinity of 1 to b, negative 1 over n. So that's the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. So the limit as b goes to infinity of 1 over b is 1 over something large. That goes to 0. These two negatives make a positive, and 1 over 1 is 1. So the limit is 1. So this integral converges. So that means the series converges by the integral test. And again, understand that this series, the sum, I don't know the sum of this series. I have no idea what it is. Some people think, oh, well, it must be 1. No, it's not necessarily 1, okay? All this integral test can tell you is that since this integral converges, the series converges, all right? It doesn't tell you what that series converges to, okay? And that's it for the integral test. As always, thanks for clicking.